In this video, we're going to look at where the kinematics equations for constant acceleration come from. So there's three kinematics equations that are really useful for situations where you're accelerating at a constant rate. The first one is that your final velocity, so after some time has gone by, your v2, will equal your initial velocity, whatever you started with, plus your acceleration multiplied by however much time went by here. That equation actually comes from the definition of acceleration. So the definition of acceleration, which is that A is equal to the change in velocity divided by the change in time. We're going to rearrange this just for delta V, get the delta t off the bottom, it'll just look nicer. So we'll get that done first. That cancels out our delta t on the bottom. And we get on this side, acceleration times delta t is equal to our change in velocity. Right, now what is change in velocity? So change in, the delta sign there, means the final thing minus the initial thing. So change in velocity means final velocity, v2, minus your initial velocity, v1. So delta v is v2 minus v1. So what I'm going to do is take this definition of change in velocity and just sneak it in here, replace my delta v with that. So I'll get A, acceleration times delta t, is equal to my v2 minus v1. The last step is just to clean things up. I want to get v1 on the other side. It's being subtracted here, so I'm going to add it to the other side. I get acceleration times time plus my v1 will give me my v2 here. And then my last step is just to write it forward so that it looks nice. So v2 on the left side is equal to v1 plus a delta t. And that is your first kinematics equation. Really handy because it's a nice, simple, easy one to use. If you know three of these things, of the final velocity, initial velocity, acceleration, or time, then you can find the fourth thing. Very helpful equation. All right, our next kinematics equation is a little bit longer, so you can guess it's a little bit harder to get to, but still very possible. So for this one, you're actually going to start with your definition of average velocity. So the definition, not of change in velocity like we did before, but of average velocity. And that is that average velocity, I'll do it in purple maybe here. So V average, oh that's an AVG, average is delta D, your change in position, over your change in time. The next thing I'm going to do is just make things look cleaner, multiply both sides by delta t, get it off the bottom. It's never nice to have something in the bottom of a fraction if you can avoid it. So that gets rid of my delta t here. So I have delta t multiplied by V average is going to be equal to delta d, my change in position. All right, what is average velocity though? So we said that change in velocity was v2 minus v1, right? Average velocity, an average, you sort of add up all the things and divide by the number of them. For average velocity, if you have constant acceleration, then average velocity is actually just a half times v1 plus v2. Basically add up your initial and your final velocity, divide by 2, and you'll get the average. You can kind of picture it on a graph. Here's a velocity versus time graph. Maybe here's a changing velocity, so that's a constant acceleration. You start with some v1, you reach some final v2, and what you want to know is, well, what's the average? What's sort of that middle line, v average? We don't want to know the change in velocity, we don't want to know how far we've gone, we just want to know what the middle is. So that's going to be take your initial point, your final point, divide by 2, and you'll get the middle line. So I'll replace V average with half times V1 plus V2. So I'll have delta t times 1/2 times V1 plus V2, and that all equals delta d. The next thing I'm going to do is actually just look a little closer at that V2. So V2, we actually have a definition for V2 that we just came up with. Our first kinematics equation defines V2 as the initial velocity plus the acceleration times delta t. So V2 here is V1 plus the acceleration times delta t. Then I can actually replace V2 with all that stuff, and that's what I'm going to do next. So here I have delta t times a half times my V1 plus, and then instead of writing V2, I'm going to write in all the stuff that V2 is, which is V1 plus a delta t. And all of that still just equals delta d on this side. That hasn't changed. Okay, let's clean up the inside of this brackets a little bit. So out front I have a half delta t. I'll just write that in a nicer order. It looks prettier like that. And then in my brackets I have v1 plus v1. That's 2v1, right? And then I have the a delta t. And all of that equals delta d over here. Let's do a distributive property. So we're going to take our half delta t and multiply it into our brackets, multiply it by both terms. So a half delta t times our 2v1 is going to be a half times the 2v1 times delta t. That's our first bracket. Our next one, we're going to have a half times an a and a delta t, and then another delta t makes delta t squared, right? So a half, the delta t's multiplied by each other make a delta t squared, and an acceleration is all in that term. And on this side, I still have just delta d. I'm going to expand that though. A change in position is a d2 minus a d1. Let's clean things up a little bit here. This term is already nicely cleaned up. This term needs a bit of work. I've got a half and I have a 2. Those cancel out. So I just have v1 delta t here. The other thing I'm going to do is move this negative d1 to the other side. So I'll get positive d1 on this side, plus my v1 delta t, so the half and the 2 canceled, plus my half a delta t squared, and that all equals d2. And then just rewrite it forward. So I get d2 is d1 plus v1 delta t plus a half times the acceleration times delta t squared. And that is my second kinematics equation right there. So let's just go over where that came from again. We started with the definition of average velocity. We replaced average velocity with the initial plus the final velocity over 2. Then we replaced v2 with our first kinematics equation, right? So this here is our first kinematics equation. Once we snuck that in there, we simplified the inside of our brackets first. Then we used distributive property to bring in the half times delta t here, multiplied it by the first term, multiplied it by the second term. That gave us a half times 2, just canceled out. So there's just left a v1 and a delta t in the first term. The second term we had a half times the acceleration times delta t makes delta t squared. We expanded out our delta d into d2 minus d1 and moved the d1 to the other side, and that gave us our second kinematics equation. The last kinematics equation is really handy for situations where you don't know the time. And in fact, this kinematics equation actually comes from kinematics equation 1. So equation 1 is that v2 is v1 plus a delta t, and equation number 2, which is d2 is d1 plus v1 delta t plus a half a delta t squared. And what we do to create our third kinematics equation is we actually rearrange this one for delta t. So we isolate for delta t here, and then once I have equation 1 rearranged for delta t, I'm going to plug it in for delta t everywhere there's a delta t in equation 2, here and here, right? Then I do a little bit of fancy algebra, sort of rearrange things until I have v2 squared on one side and everything else on the other side, and it turns out you'll actually create this third kinematics equation. I'm not going to show you all that algebra though, because that is your assignment for this unit, so I will let you figure that out on your own.